Okay, so there are just a very small handful of things I wanted to just talk about at the end of chapter 7 before we continue into chapter 8. I should mention that I should have really, and I thought I did, assign chapter 8 reading over the weekend, but I didn't. So you should do it before Wednesday, whenever you want to do that first 4 sections. I thought I put it on the website, but now all the videos are up there if you want to watch those videos and that kind of stuff, and post before Wednesday, 8 a.m. So the usual kind of thing. The worksheet we were working on, we're not going to do these problems together, but these problems were on the back side and they have to do with two-dimensional collisions. So I just want to kind of think about this. They're in principle no more complicated than the ones we've been doing. They just have an extra dimension in there. So there's a little bit of extra algebraic stuff to be done. So here we've got the before picture. There are a car and a truck heading towards an intersection in perpendicular directions. 800 kilogram car traveling in the plus x direction at 10 meters per second, and it's going to collide with a 1200 kilogram truck traveling at 8 meters per second in the plus y direction. So this is here's my axes. Here's what it looks like before the collision. They don't stick together in this particular problem. So we're not talking about a completely inelastic collision, but it's going to be partially inelastic if it's at all realistic. Car collisions are never explosive. It's observed that the truck ends up moving in the plus x direction. So the 1200 kilogram truck is moving in the plus x direction afterwards at 5 meters per second. And the question is, what is the final velocity of the car? And probably the easiest way to get that final velocity is just to give, if you're asked for a velocity, you need to give the vector, and giving the x and y components of the velocity afterwards would be sufficient. Okay, so all I'm going to do, we weren't told that it's an elastic collision. Collisions between cars are very seldom elastic because of the crumpling metal loses energy. But we do, it seems reasonable. They're probably skidding, but even so, if we apply the impulse approximation compared to the impulse delivered to each of those two objects from the other, that contact force, the impulse delivered from the skidding tires even is going to be really small. So it's pretty ignorable if you go from just before the collision till just after the collision. Momentum is approximately conserved. Okay, so all I'm going to do, and I'm not going to talk too much more about this, but I'm going to say that the total initial x momentum is equal to the total final x momentum. That means I have to add up the mvx's for the two objects, right? So initially, in terms of x components, well, the 1200 was only moving in the y, so its x component of momentum is 0. But here's the car's x component of momentum. We know the final x momentum of the truck because it was moving all in the x direction, and we just put an unknown there. And that's the only unknown in this equation for the car, its final x velocity component. So I could solve for it. Same thing happens with the y components, right? I just demand the initial y component of momentum total is equal to the final, and I can find the car's final y velocity component. And then we're asked for the velocity, that's a vector, but giving the components of a vector is a very complete way to do that. So I was reminded of this because there's a problem on the homework where if you've looked at the homework, where a ball is coming up and bouncing off of a wall kind of vertically like that. So it's actually moving in 2 dimensions. Turns out in that case with the collision, the y momentum doesn't change at all, you can see, but the x momentum does change. So it's in principle even easier to think about than this particular problem here. And I should say problem 2 is also on the backside, and was no more, I think it was they stick together afterwards. So it was completely inelastic rather than being just partially inelastic. These were some people's, I'm sorry, it's such an extreme aspect angle. It's better to see this over here. Couple of reading response questions. Why does a head-on collision function differently than the ones where the objects are traveling at intersecting angles to one another? And the answer is, well, as long as you're given all the angles and you can figure out x and y components before, and that would allow you to figure out x and y components afterwards, it's in principle no different. It's a little bit simpler if everything moves only along the x direction, both in and going out, because then you don't have to worry about y components. So, but other than that, it's no more complicated in principle, as you can see from that example we just did. You're just repeating things for X and Y. Would we ever calculate anything like the problem where a projectile is launched into a mass on a pendulum where the mass goes through the mass? I assume that means it blasts it's kind of like the ballistic pendulum, but it makes it all the way through and blasts out the backside. If someone who's looked at all the homework, is there a problem in the homework? I have a vague memory of something being shot through a block. Is that in the homework? Oh, okay. Yeah, I mean, you know, a particular example, this may be a good time for me to check the aim of the camera. I don't know why, it looks a little blurry too. Is it okay? Maybe it's okay. You know, you could imagine a bullet going at a very high speed, you know, 1,000 meters per second, and we're given the mass of the bullet, we'll just call that little m. It's flying along, and here on some surface, I've got a big block of mass m, and it's just sitting there initially. It's not focused on here. Let me just, sometimes what works is if you stop the video and then start the video again. Maybe that's better. Yeah, I think that looks better. It must have gotten focused on me, maybe. So this is our initial condition. And then maybe afterwards, the block is observed to be moving at 8 meters per second. The bullet has burrowed all the way through and has shot out the other side, and you want to know the bullet final or something like that. Well, you can imagine using conservation of momentum there, right? It's not a completely inelastic collision. There are two different velocities in the final case, but as long as I'm given one of them, I'll have only one unknown in the conservation of momentum. So, you know, one could imagine with a ballistic pendulum like this where you shoot all the way through the block and the block still rocks up to a certain height, and therefore I could figure out from how far it rocks up what the final velocity of the block must have been, and I could still conclude what the initial you know, if I measured the, I don't know how to use this, but you know, if I knew the initial velocity of the bullet, I could conclude what the final velocity is. Yes, Sarah. I'm assuming in this problem an idealized thing where it's not blowing out any of the wood or an insignificant amount of the mass of the wood. But you know, in a real problem, if you fire through a wooden block, it's probably going to push splinters out this side. And the question is, are those negligible or not negligible? And probably in your average physics textbook problem, they're going to be negligible. Everything gets complicated when you think about it too much. Put in more and more realistic things. Okay. Where's my clicker? Here we go. Here's a couple just to end on voting questions. This is the kind of thing you've seen, you know, the annoying carnival game where you try to knock down those little things with the baseball, but they've got the fuzz around the outside and it's much harder to hit them than it looks like it's going to be. So here's something similar, but physics-sized. A person attempts to knock down a large wooden bowling pin by throwing a ball at it. The person has two balls of equal size and mass. One is made of rubber and the other one is made of putty. So putty is supposed to be not very elastic. It doesn't bounce very well. I brought some balls that are kind of elastic. Golf balls are pretty elastic. They bounce really well. And this is a ball that I bought because it's sort of like what you would expect the putty to do, just thud on the ground. So golf balls, we all know, bounce really well. This is made of some, I don't know, maybe a material that's like those memory pillows where when you push on it, it doesn't spring back. So it just kind of like doesn't bounce much. Maybe even putty might just go thud and not bounce at all. So a big difference in how they bounce. And the question is, which one of these is going to be more effective? Assuming they're the same mass, you can throw them at the same speed. Which one would you choose? Which is most likely to topple the bowling pin if you throw it directly at the front of it? The one that thuds into it like the piece of putty, or the one that's really bouncy? I would suggest just go with your intuition. We'll see if your intuition is correct. You know, there are several people looking through their notes, but if you've got to vote, just vote with your gut and we'll see how it ends up. I'm seeing almost all B's. I think I saw 1 or 2s. I saw 1, 1. And 1 is actually the correct answer in this case. That's why it's a great voting question, because it sort of goes the exact opposite of your intuition. Somehow I have the intuition even, you know, if something, if it sticks to it, it's giving it a lot of oomph and it just keeps pushing on it right after it's stuck to it. But, you know, you can imagine there's not much effect coming from the floor. As this thing comes in and knocks to it, momentum is going to be very close to conserved in that collision. And so what my goal is to knock this thing over is to transfer as much momentum to the bowling pin as possible, okay? So that means if the bowling pin has 0 momentum to begin with, the more I can change the momentum of the object that's coming in and hitting the bowling pin, the more the bowling pin's going to have to change its momentum. If you like, in terms of when we derived the principle of the conservation of momentum, at one point along the way, I didn't really remark on it too much, but we were talking about 2 objects that were colliding with each other. So in this case, it could be the ball and the pin. And just 2 steps away from the conservation momentum is that the change in the momentum of one object is equal and opposite to the change in momentum of the other. So if the ball that's coming in changes by 3 meters per second in that direction, that means the thing it ran into is going to have to change by 3 meters per second in that direction to conserve momentum, right? X components, for example. So in this case, it goes back to that question of, in which case does the ball have the greatest change in momentum? Is it when it essentially comes to rest at the end, or when it goes in and bounces back? I think we had a voting question about this on Friday, right? Where we talked about stopping a ball that was going at speed v, speeding it up to speed v, or stopping it and then speeding it back up to speed v. So in this case, if we have an elastic ball, the bouncy ball, that comes in and bounces back, the more it bounces back, the bigger the change in momentum of the ball that's hitting it, if you remember that voting question. That means the bigger the change in momentum of the thing it's running into. And if it started off with 0 momentum, I only want to make its change in momentum bigger to make it be moving faster in the final state and have a greater chance of falling over. So you don't want that kind of putty ball that just slaps down on the floor or slaps, you know, attaches to the object. You want something that bounces back, because that's going to give more momentum to the other object in that direction. Any questions on that one? Okay. One more, I think this is the last thing for chapter 7. Is it possible for a stationary object that is struck by a moving object to have a larger final momentum than the initial momentum of the incoming object? Yes or no? Okay, maybe instead of voting, because a lot of people don't look like they're ready to vote, anybody want to try to explain what they're thinking? Yes, Edward Lee. Yeah, I mean, my intuition, again, would agree with you. And unfortunately, or fortunately, if you like surprises, that's not true in this case. And it's, again, just like that, the previous case is counterintuitive. If you think of something sort of changing directions, we would think, hey, it's moving at the same speed. It's got the same momentum before and after. No, there's a huge change in X momentum if you completely change direction, much bigger than if you come in and stop. We can use the same kind of principle here and analyze a very specific kind of interaction. Let's imagine we have out floating in space, here's a big bowling ball, right? It's just sitting there from our perspective. And here is a little tiny ping pong ball, nice and bouncy, coming in with some momentum. We'll just call it P, its initial momentum, right? Now, this big bowling ball is just like a brick wall as seen by this thing, right? And if it's a pretty bouncy ping pong ball, if it comes in with momentum P to the right, it's going to leave approximately with momentum P to the left. That's going to be just a little bit off, but the bigger I make the one mass, the more it's going to be like a brick wall. So we can make it really close to this kind of situation where it just reverses directions. Now notice, this one comes in with momentum P. What's the change in momentum from before to after for the ping pong ball in terms of P? How big is the magnitude of the change in momentum? Yeah, it's not just P, it's 2P, right? Because if it changed by P, then this thing would come to rest. But in being projected back again, that's a change of 2P. That's what the case where we were looking at those three cases. So this one's momentum changes by 2P. That means this one's momentum's got to change by 2P. And if it starts at rest, the only way for it to change by 2P is to be moving with momentum 2P afterwards. And so it does sound like somehow it violates the law of conservation of momentum. The problem is we're not thinking of, it's sort of like we think, oh, the momentum of this is going to get all used up, and that's the worst case scenario. But getting all used up isn't the worst case scenario, because you have an even bigger change in momentum when you bounce back. Most people aren't considering, if we're talking about the x-axis here, that this could go from a positive x component to a negative x component and really have a much bigger change in momentum, right? In this case. So that's a case where that's true. So maybe that's the cautionary tale of, if you think momentum is intuitive, it's not nearly as intuitive as, position, velocity, even energy to most people. But it's easy to apply. The equations for applying conservation of momentum aren't too complicated. It's always going to move, I was imagining it out in empty space and just sitting there, and the ping pong ball is bouncing off of it. Now, to the ping pong ball, it's not going to notice the fact that this huge thing moves a little bit. But the ping pong ball changes momentum, so the bowling ball's got to change momentum. Now, it's not going to move much. So
I guess I'm just not following back like it has to change momentum.
well, so most people's intuition about momentum, what things would look like if it weren't conserved, usually tell you that, right? If you had a bowling ball here floating in empty space, right? And we throw a baseball at it and the baseball bounces back in that direction. Would you be surprised if the bowling ball just sat here and it wasn't pushing up against anything? There was nothing holding it in place. To me, that would seem to violate my intuition, right? I sort of know what it looks like for momentum to not be conserved, and it doesn't look right. So if I throw a baseball at it, I expect it to move substantially because a baseball is, a not insignificant fraction of its mass. Now, the ping pong ball, just in principle, is a much smaller mass. And so that means that the final motion of the bowling ball is going to be much less. But still, it's more than the initial momentum of the ping pong ball, because the change in momentum of the ping pong ball is bigger than its initial momentum. And when something starts at rest, and if it's going to change by a certain amount, the only way is to end up with a final momentum of that amount. So this one, the ping pong ball comes in with momentum P, it changes by 2P. This one starts at rest, and so its final momentum must be 2P. All right. Other questions on this one? Okay, let's go into chapter 8. You can, if you haven't read it yet, that's fine. Just let it wash over you. We're just talking about some kind of introductory kind of stuff. It gets increasingly, detailed as the chapter goes on, but we're just going to introduce new units for angle measurements now of radians, things like that. So we're going to be talking about rotations, and most of what we're going to talk about in this chapter concerns fixed rotation axis. So we're going to imagine something rotating, and it's rotating around a point on the body. You can even think of there being an axis rigidly attached to the object. and it's spinning around that axis. It does not have to be circular or spherical or anything like that. It could have a really oddball shape, so a lot of times when people are thinking of rotations, they think of nice circular wheels like this, as is pictured up there. But it could be something really weird like this cutout. I made this cutout of Kentucky for another purpose, but it could be a weird thing rotating like this, right? The axis of rotation, which is where this pin is not changing. So this would be an example of a fixed axis of rotation. That's the kind of thing we're going to be almost exclusively sticking to. We'll change that slightly at the end. Now, the confusing thing, or at least possibly confusing thing, is that as this thing rotates, let's imagine it's rotating at a certain number of RPMs, revolutions per minute. Not every point on this disk is moving at the same speed. Points on the outer edge of the disk are moving really quickly. But if you imagine, maybe it rotates once every second. So in 1 second, this thing goes a pretty big distance all the way around. Whereas in 1 second, this point right in the middle hardly goes any distance at all, right? So its literal speed, how fast it's moving through space, is much smaller as you get closer to the center. One of the things we're going to want to investigate very early on is, if you know the rate of rotation, like sort of an RPM kind of rate, how can you figure out what the usual linear speeds are of different points on the rotating object? Before we get there, we need to talk about radians. And many of you have heard about radians before, but many of you are also not used to using them, which is one reason to put them off for a little while till later on in the course. But they're going to make our equations simpler now, so it's time to specialize to radians, at least for these rotation problems. So we've already measured angles in 2 ways. You might think, oh, we've been sticking to degrees, but not necessarily. We've been talking about revolutions along the way too. And revolutions is a perfectly good rotation angle measure, right? 1 revolution means the same thing as 360 degrees. A half a revolution is the same as 180 degrees. So we can measure all our angles in rotations if we want. But here we're going to use and motivate why it's useful a 3rd angle unit, which is called radians. And the definition of radians is, if you have a little circle right here, and you draw out from the center to the edge of the circle, the radius r, and then you draw the arc length that is subtended on the circle by a certain angle theta. So I've got 3 things drawn on there: arc length s, theta, and r. Then the definition of how to measure theta in radians is just the ratio of the arc length distance to the radial distance. Okay, and clearly as theta gets bigger, r isn't going to change, but s is going to get bigger and bigger, right? So theta in radians is going to get bigger and bigger. The picture here shows, most people don't have a good intuition about radians, but the picture here is showing an angle that's about 1 radian. 1 radian would be when s equals r, right? And this picture, it looks like r is about the same as s. So that's about 1 radian in terms of angle there, right? 2 radians is when s is double r, so 2 radians would be an angle, somewhere ending here, that angle all the way from there over there, and so on. How will we figure out how many radians are in 1 complete revolution? In other words, how many radians equals 360 degrees? Edward Lee? 2? Well, I don't think so, because what's pictured here is about 1 radian. So 2 radians would be an angle twice as big. It might go from this horizontal one up, I didn't draw it here, but about to right there. It is very close to 6. Are you just eyeballing that? Yeah, it's very close to 6. Anybody know what the exact number is? Yeah. 2 pi, right? And pi is close to 3, so 2 pi is close to 6. So that's good estimating there. And a lot of times it's very useful to remember pi is almost 3. So I can sort of have an idea in my head how big things are. Here's how I could calculate it, right? We could just literally do this calculation. The arc length in a complete circle is 2 pi r, right? That's how big you have to go, or how big of a distance you go going all the way around to where you started. And if we divide that by r, the r's cancel and you get 2 pi. So 2 pi radians in a complete circle, pi radians in half a circle, right? 90 degrees is pi over 2 radians. Here's maybe a tough one or something we have to think about. What about if I give you just an oddball angle? 42 degrees. Like wheel rotates through 42 degrees. How do I figure out how many radians that is? Anybody have an idea of how to do that? Some of you probably do this kind of stuff in your science classes. That's not a good pen. Yes, Austin. Yeah, so we're just going to say, we just said what was the same thing in radians and degrees. So in this case, what I can do is, let me, just so I have a nice normal unit here, I'm going to put DEG for degree. 42 degrees, and just like we did almost, it was probably day 2 of the class material, we're going to multiply by 1 there in a ratio where the numerator and denominator are exactly the same thing in such a way that the degrees cancel. And so what we want to do is, what Austin was suggesting is that pi radians, we just said, is the same thing as 180 degrees. And then the degrees cancel out like that. And I can put the number in my calculator and see what it is. So it literally is a different unit in this case. And when we want to change from degrees to radians, we do that process. So this is about 0.7 radians, a little bit less than 1 radian. Okay, so that's radians. We'll see why we're interested in them in a bit. Okay, now, theta is kind of like position. In other words, when we were back when we were talking about motion in 1 dimension, right? We would say, we're going to measure our position on the x-axis by x. In the same way, we might consider looking at this rotating wheel here and saying, I've got a little white point marked on the wheel, and saying, as time goes on, just like something might move along the x-axis, this white point, instead of moving in x, it's moving in angle, theta. Maybe I say theta is equal to 0 over here. So theta keeps getting bigger and bigger and bigger as time goes on. So it's just a different kind of movement through position, but instead of the usual old linear position we've been talking about so far, we are talking about angular position. So we're going to think of it the same way, and we're actually going to use that to make the same kinds of definitions, because we'd like something that tells us not only what position we're at. We're going to say, where's that little white dot? Well, we're going to specify by saying, well, maybe to my right is measure the reference point for theta equals 0. We're just going to say what angle it's at by giving an angle relative to there. We would also like to be able to say how fast is it rotating. Okay, and just by analogy with what we did before, we said when we were talking about x as linear position, the rate at which x changed, delta x over delta t, was our average velocity. And then we took that over a very small amount of time, and we called that the instantaneous velocity. Here we're going to do exactly the analogous thing, except instead of change in position, we're going to have change in angle. So this is the Greek lowercase letter omega. Looks like a curly W, but we usually don't pronounce it as W. So the average omega, average angular velocity, which is going to tell us how fast it's rotating, is the angle it rotates through divided by the amount of time it took to rotate through that angle for a finite amount of time. And then, just like for average velocity, nobody really cares, or it's not so useful to know about average angular velocity. We want to know right now, as this thing is slowing down, what is its angular velocity right at an instant of time? And so what we're going to do is take a period of time that includes the time you want and let the amount of time you change go to 0. And then the change in theta is also going to get really small, and that ratio presumably approaches a perfectly finite limit, which is the angular velocity. As opposed to linear velocity we were talking about before, this is angular velocity. And it tells us not only how fast it's rotating, but in which direction it's rotating. Okay? The how fast is just how big this number is, right? So this could be it. If my theta is measured in radians, this might be in radians per second. If my theta were measured in degrees, this would be in degrees per second. But those are telling me how fast this thing is moving around, how fast the angle is changing. It tells me how fast, but it also tells me in which direction it's spinning, in the sense that if I know which way is the positive direction, so usually in your math classes, if you've talked about rotations in a math class before, you usually talk about counterclockwise rotations being positive. We'll always specify because we can't really be sure, but as this thing's rotating around, maybe I'll say, okay, I'm going to call the angle theta equals 0 over here, and I'm going to call a counterclockwise rotation from there a positive angle. And so if omega is positive, that means it's rotating in the increasing angle direction. And if omega is negative, that means it's rotating in the decreasing angle direction. So it also tells us, just like the velocity x component tells us about which direction it's moving by the sign, the angular velocity sign tells us which direction it's rotating, as long as you know where 0 is and which is the positive angle direction. We'll be careful to specify those. Okay, similarly, I know we're going much faster than we did back in the day in chapter 2 and chapter 3, but we can make an analogy to acceleration, right? Acceleration was the rate of change of velocity. So we first defined the average linear acceleration as delta v over delta t. Here we can define the average angular acceleration, which is given the symbol alpha, lowercase alpha, as delta omega over delta t. And again, nobody cares about that. We immediately let delta t go to 0 because we want to be able to talk about instantaneous angular acceleration. And just like, regular acceleration is a little bit less intuitive than velocity, or quite a bit less intuitive, it's the same way with angular acceleration. You might have to think about it because it depends, sometimes the interpretation it depends on which way it's rotating. So it does give us the information about the rate at which omega is changing, and also the direction in which omega is changing by the sign of alpha. For example, the easiest case, right, is if we think about, well, what if I have, I know which way on my rotating object is the positive rotation direction. You have to know which direction is increasing angle. If the angular velocity is positive, if it's rotating more and more in the positive direction, in other words, it's spinning so that theta is increasing, and you have a positive alpha, that means it's speeding up, right? That means its omega is positive, but omega is getting bigger and bigger and bigger as time goes on. So that means it starts out slow and it's going faster and faster and faster in the positive direction as time goes on. Again, if we have a positive alpha, and if omega happens to be negative, it's slowing down. And maybe the best way to think of these is the way I talked about, thinking of acceleration as a trending. Both of these cases are trending towards positive omega. If omega is positive and you have a positive angular acceleration, it's only going to get more and more positive. So it's trending more towards more positive omega. If omega is negative and you have a positive alpha, and that's positive is the way that omega is trending, then we can say my omega is negative. The only way I can get to a positive omega is to slow down. So in one way, the sign of alpha tells us about the direction in which omega is trending. Yeah. If it's speeding up or slowing down, it's not. And you remember that we talked very briefly about non-uniform circular motion. In uniform circular motion, the acceleration of a point is all that's moving is always towards the center of the circle. If it's speeding up, then it tilts a little bit. The acceleration tilts towards the direction that it's speeding up. If it's slowing down, the other. Now, just to make sure, we're not talking about here the direction of the good old acceleration. Here we're talking about angular acceleration. Okay, so it's different than linear acceleration, but it tells us about how fast and in which direction the angular velocity is changing. You can imagine, so you can test yourself. What about if alpha is negative and omega is positive? Well, if alpha is negative and omega is positive, then that means it's actually slowing down in the positive direction because it should be trending towards the negative. At least for me, that helps me to sort it out. Other questions on this before we move on? Okay. Now, can't quite see on here. I don't want to, oh, here we go, X that out, there we go. Now, now that we've defined omega, omega is going to tell me at any instant how fast this thing is rotating around the fixed axis. And of course, the faster omega is, the faster, these points on the disk are going to move, right? If I double omega, if I double the RPM rate, it seems like I'm going to double the speeds. So what's the relationship between the speed of a point on the disk and the rotational rate? We want to know the relations between angular and linear quantities. Here, linear just means the good old-fashioned ones that we used before. So here I'm asking the question, if I want to know, so, this is sort of a degenerate case, but if I want to know the relationship between angle, that's an angular position, and how far it moved, that's a linear position, right? How far you moved, linear displacement versus angular displacement. The relationship between those, we already know. It's given by our definition of theta in radians, if you think about it, right? How is delta theta related to delta S shown on here, that arc length? Oh, well, that's just the definition of delta theta in radians is delta S over R. As long as we measure theta in radians, we can solve for delta S, and this is expressing how far it moved in terms of how far the angle moved. We have to multiply by R, and we have to measure the angle in radians. You could re-express this in degrees, but it would just make the equation more complicated. So we're going to leave it as everyone does and always measure angles in radians there. Okay, so now somehow lost control. Now we want to, well, first of all, think of, a lot of times when people see these images, they think, oh, it only applies to the point on the edge of the wheel. No, it doesn't apply to the point on the edge of the wheel. And R, if you're talking about a disk, R isn't always the radius of the disk. We might be interested in how far this point moves when the angle changes by delta theta. And this point's going to move a smaller distance than the one that was out here on the outside, right? The relevant R to use is how far the point you're interested in is from the point of rotation. In fact, the outside of that thing doesn't have to be a regular circle at all. It could be some weird thing, like this Kentucky state cutout here, where, yes, even though the outside doesn't have a nice shape, if you watch any point as it goes around, it's going to be moving in a circle as time goes on. So it may as well be part of a disk, right? But it's good to remember that it could be some oddball shape here. So as we're looking at some point on here, now, so we found out the relationship between linear displacement, how far you moved, and angular displacement, how far it rotated, right? There's a definite relationship. They're proportional to each other. The next thing I want to address here is the relationship between how fast this is going and the angular rotation rate, omega. Clearly, the bigger omega is, the bigger V is going to be for any point on there. But there's going to be different V's. Points that are further out are going to be going faster. Points that are closer in are going to be going more slowly. Let's get to that by our good old definition of average speed, which is if something is moving, the average speed between two times is how far it moved divided by the amount of time that elapsed. And in this case, how far it moved is given by this delta S, right? It's moving on a circular arc as that thing rotates around its fixed axis. Now, we just found out that the relationship between delta S and delta theta can be substituted up there in the numerator. And then I've got something that looks like delta theta over delta t, and that's like an average angular acceleration. So this is telling us that the average speed of this point is its R value, that means how far it is from the axis of rotation, times the average angular velocity of the object as it's rotating. And then if you let delta t go to 0, that's also telling us that the instantaneous speed is equal to R times the instantaneous omega. So if you tell me at any time how fast it's rotating in radians per second, then I can tell you how fast it's moving in meters per second. Okay. Because we use this relationship to get this relationship here, this one's only valid if we put omega in radians units. Just like this one's only valid if maybe I should put a subscript of radians on omega. It's got to be measured in something like radians per second. That's a rate of rotation, okay? Because it came from this relationship, which is assuming that. Similarly, we want to know this point's accelerating, right? It's certainly accelerating along the direction towards the center of the circle because it's moving on a circular arc. It may also have a tangential component of the acceleration if it's speeding up as time goes on. So we want to know what's the relationship between the radial acceleration and the tangential acceleration and the angular acceleration. Okay, let's start with the tangential component of the acceleration. We called that earlier AT. So we say, at any instant, say at this instant, the radial direction means radially inward towards the center of the circle, and the tangential direction is tangent to the circle that it's traveling on in the direction that it's moving. So to figure out the tangential acceleration, back when we talked about non-uniform circular motion, we just said that tells us the rate at which the speed is changing. If the speed's not changing at all, then there's zero tangential acceleration. It's all towards the center. That's why we called it centripetal in that case. But if the speed is changing, that gives us the component of the tangential component of the acceleration. So the tangential average acceleration is delta V over delta T. We just found out that V is equal to R omega, and therefore delta V is equal to R times delta omega, right? Delta just means final minus initial. So just substituting that in there. And delta omega over delta T is the average alpha. And then I can let delta T get smaller and smaller, and we'll find out that the tangential acceleration is R times alpha. Remember, alpha tells us how fast the rotational rate is increasing. So we're not talking about constant rotational rate. We're talking about something that's going slower and then faster and faster and faster. And this is telling us if we want to know how fast a point on the rim is speeding up, we can take the angular acceleration and multiply it by the radial distance of that point we're interested in from the center. Okay, I know this is kind of a lot all at once, especially if you didn't do the reading. But we're building up some definitions from which we can do a whole lot of problems. So we will be practicing with problems. It's not clear we're going to get to them today. Similarly, we talked about when we were looking at non-uniform circular motion that the radial component of the acceleration doesn't change from the case of what it is when it's in uniform circular motion. Even if you're in non-uniform circular motion, the centripetal component or the radial component of the acceleration is still v squared over r, even if you're speeding up or slowing down as time goes on. The difference is I can now express v as the linear quantity. I want to re-express it in terms of an angular quantity. And we know v equals r omega, so I can just substitute that in there, square this out. One of the r's cancels between the numerator and denominator, and we find out that the radial component of the acceleration is equal to r omega squared. So all four of these are relationships on the left-hand side of linear quantities that we talked about before, how far you moved, how fast you're moving, and two components of the acceleration, and the corresponding angular quantities that they're related to. Okay. Best to remember, again, all of these flowed from this up here. We assumed this to get this, and then we assumed this to get these two, and therefore all of these depend on being measured in radians units. This alpha, which would have SI units of radians per second squared, you can't put it in degrees per second squared, or this equation isn't quite right. We'd have to modify it with an extra number in it, like to change units, essentially. All right. Yes. All four of those, they would be, you could write them for degrees, but they'd just be a bit more complicated, and people like the minimalist versions. Okay, we do have a worksheet to do with this. I don't know that we have time to work on it now, but in the same way that when we assumed, we're again thinking of theta as an angular position, just like we have linear position. Edward Lee?
What are the units for acceleration and velocity?
In, are you talking about the angular velocity and the angular acceleration? Yeah, so in SI units, let me, for the sake of the video, stop sharing. The SI units for theta would be radians. For omega, radians per second. And for alpha, radians per second squared. So just like everywhere you had a position kind of thing, meters, you're having an angle instead, because we're just talking about angular position rather than linear position. Good question. Okay, so we made the assumption way back when, and we didn't show where these kinematics equations came from, but they resulted from the assumption that the acceleration is constant. Okay, so looking at the ones on the right, which are old friends, we assumed the acceleration was constant, and we figured out how, or somebody who did some calculus figured out how x varies with time, how Vx varies with time, and then we substituted one into the other one and to eliminate the time, and figured out how Vx depends on how far it's been displaced. Exactly the same derivations, but just with the names changed, would follow from the assumption alpha equals a constant over here. If you've got constant angular acceleration, that might mean that something starts from rest and keeps speeding up and speeding up and speeding up in a constant kind of way, the same way something might speed up with constant linear acceleration moving on the x-axis. Notice what's changing between the left side and the right-hand side. They're the same equations, but everywhere you have a linear quantity on the right, you have an angular quantity on the left. So angular position equals initial angular position plus angular rotation rate times t plus 1/2 angular acceleration times t squared. You're just replacing all of those things with their angular analogy. Third one, final angular velocity squared equals initial angular velocity squared plus 2 alpha delta theta. That was a delta x before. Okay, so again, there's not really new kinematics equations to memorize as long as you understand that the theta, omega, and alpha are analogous to x, vx, and ax. They're just a different kind of position, if you like, telling us where we are in angle or in rotation rather than where we are on an axis. Okay, we've got about 3 minutes left, and maybe we better just hand back the exams and we can do this on Wednesday so we're not rushing it too much. I'll pass out this worksheet and we can start practicing with that. I'll try to get, for those who really want to get ahead on the homework, I'll try to post a chapter 8 homework assignment that you might be able to start working on some of the early ones if you like.